Good afternoon, everyone. My name's Hannah, and I'm an applications engineer at Plasma Technology. And today I'm going to be talking to you about advances in plasma-enhanced chemical vapor deposition. So, just to give you a brief overview of the presentation, I'm going to start by giving an introduction and talking a little bit about the semiconductor industry and how it's changed, and the importance of chemical vapor deposition and other deposition techniques to this industry. I'll briefly explain chemical vapor deposition before I go on to talk about plasma, so how we use it and why we use it. And then I will talk about two different methods of plasma production. So I'll talk about capacitively coupled plasma with PECVD and inductively coupled plasma with ICP CVD. Okay, so just for a little bit of general interest, this is one of the first integrated circuits ever made. It was made by a man named John Kilby in 1958, and at the time was completely revolutionary and changed the electronics industry forever. So if we compare this to the kind of things that we can create now with several billion transistors on a single microchip and feature widths that are regularly in the nano and micrometer scale, you can really see just how far we've come. Now, in order for these advances to continue, we need to come up with new and novel methods of semiconductor fabrication. And one very important branch of semiconductor fabrication is deposition, because it's used to create insulating and conductive layers between circuits, and also to provide protection from the surrounding environment. So at Plasma, we offer a number of deposition and growth tools. So we've heard about ALD and nanostructure growth tools. We also do physical vapor deposition and ion beam deposition, and the technique that I'm talking to you about today, which is plasma-enhanced chemical vapor deposition. So before I talk about plasma-enhanced chemical vapor deposition, I'm briefly going to tell you about chemical vapor deposition. So put very, very simply, you introduce your gases into a reaction chamber, and they react together to form a solid product which coats everything in the chamber, including your substrate, and volatile byproducts, which you can pump away so they don't get integrated into your film. Now, in order to do this, the system requires a lot of energy because you need to break the bonds that already exist in these molecules. And this is normally provided by heat. But this isn't always possible or practical, especially when you're using temperature-sensitive substrates. So when we use these, we can overcome the problem of high temperature by using plasma. So essentially, instead of using heat to provide the energy, you put electrical power into your gas, and it serves to pull it apart into electrons, ions, and neutral radicals. So inside your chamber, you have this soup of reactive species, and because everything is so ready to react, you can do lots of things at much lower temperatures. So it really widens the range of devices that you can use. So here is one of our PECVD systems. It consists of a vacuum chamber into which you pump a gas, a heated bottom electrode where your substrate sits, and a top electrode where power is supplied. Now, this has a number of really important features for plasma production. So in terms of the plasma itself, we have dual frequency power. So we have one at 13.56 megahertz and then the other one in the kilohertz range. And what this does is it allows us to control the density and the stress of the film. So when you have a very high frequency power range, it's very good at getting the electrons to move because they're really light, but you don't get that much movement of ions because they're much heavier. So when you use a lower frequency, your ions kind of have time to catch up and can be used to bombard the surface. And when they do this, it almost packs your film down, so you end up with a much denser and much more compressive film. And by varying high frequency and low frequency pulse times, you can tune your films all the way from compressive to low stress to tensile. So the other important feature when it comes to plasma production is a fast-matching AMU unit, so a fast-matching auto-match. This is really, really important because if your auto-match unit doesn't match the impedance of the plasma, you get a lot of reflected power back into your generator, which is, one, not very good to the generator, and it also means that the power you're asking for in the software isn't being delivered to your plasma. So by having a really quick auto-match unit, you're taking out a lot of the uncertainty in the process, so it's much more repeatable. Another important feature of films is the uniformity. So in order to ensure that we have good uniformity, the heated bottom electrode has very, very good temperature uniformity. So if you have an electrode with lots of fluctuations across temperature, you end up with different growth rates because the rate of growth is dependent on temperature. So in order to achieve good across-wafer uniformity and also wafer-to-wafer uniformity, it's really crucial that your bottom electrode is uniformly heated. The second thing we have to increase uniformity is this shower head. So rather than the gases all being pumped into here and sitting around in the center and then slowly diffusing out in your chamber, we instead force them to come through the shower head, and that creates a really, really uniform gas distribution, so you get a much more uniform plasma. So a really good example of the kind of process we can achieve with that system is our high-rate silicon dioxide process. So we range from low rate at around 50 nanometers a minute all the way up to super high rate at over a micrometer a minute. So for super high rate, you want things like higher flow MFCs so that you can really control the amount of gas going into your chamber. You need a larger pressure gauge because you're working at higher pressures, and you also need a good dry pump so that you can pump away all the byproducts that are produced during the deposition. But it uses the same hardware as I showed in the previous slide. Here are some of the results for our super high rate process. This graph here shows film thickness against distance moved across a 200 mil wafer. So we just put the wafer into the ellipsometer and measured north-south and west-east. So you can see north-south here in orange and west-east underneath it in blue. And as you can see, there's very, very good uniformity across 200 mils, and this is actually plus or minus 3% for 1.2 micrometers per minute. This here shows just how we can tune the refractive index. The graph I've chosen to use here shows the change in refractive index with the ratio of gas flows. So by changing the ratio of gas flows, you change the composition of the film, so you can easily tune the refractive index, but you can also tune it with the pressure and the power. And finally, at the bottom here, I've got some SEM images of a gap fill process. This again was 1.2 micrometers per minute, and you can see that we've got really nice conformality, and we've managed to deposit all the way to the bottom of a 12 micrometer trench. Now, these processes we generally suggest doing above 300 degrees Celsius, because below that you can get problems with film quality. So this is things like density and pinholes. However, recently there's been an emergence in things like organic LEDs and plastic electronics, and for that they require much lower temperatures to operate at. So the way that we would operate with those is by using ICP CVD. So ICP is inductively coupled power. So just like with the previous system, you have a vacuum chamber into which you flow a gas, a heated bottom electrode, and pumps attached to the system to pump all the gases through and out. The differences between the system, the main difference is the way that the plasma is produced. So with the previous system, you have two parallel plates, and you apply RF to the top of the plate, and you get a capacitively coupled plasma. However, with this system, we instead have a helical coil that surrounds the top of the chamber, and you flow a time-varying current through this, which induces a time-varying magnetic field, which then induces electric currents within the gas, and this is how you strike and sustain the plasma. So there are two main advantages to producing the plasma in this way. Firstly, you get a much more uniform plasma inside the reaction chamber. So when you have the two plates and you get capacitive coupled plasma, any difference in coupling between the two plates will mean that you have a different ion density inside your plasma, and this can cause things like attacking of the sidewalls, which one damages your machine, and if you attack them enough, you can end up with contamination in your films. So by using ICP CVD, it mitigates that problem. The second thing that this does is you can achieve much higher electron temperatures. So your electron temperature refers to how fast everything's moving and kind of gives a really good indication of how much energy is in the system. So because we can achieve higher energies inside the plasma with this system, it means we can again operate at even lower temperatures to with the previous system. So important features on this include a gas ring just above the electrode. This does two things. So it's a ring that sits above your wafer and lets the gas in. Because the gas is coming in from all sides, it gives really good uniformity. And it also means that your two process gases that come in through the top and one through the ring don't meet until they're in the bottom half of the chamber. So this means that there's much less deposition on the side walls. And when you get a lot of deposition on the side walls, it can build up and you can get flaking. So this increases the length of time you can use your tool between cleans. Okay. The other important feature of this is separate control of coil power and electrode power. So your coil power basically determines how much of your plasma you break up into a gas. So more power, more of your gas is broken up, so then you get higher rates. And your electrode power determines how much ion bombardment you get. So by biasing your electrode, you can force the ions in the plasma to move towards your substrate. And doing this, you can control, again, the density and the stress of the film. However, on the other end of the spectrum, if you have if you have a substrate that's particularly prone to damage, you can operate without any electrode power so that you don't get the ion bombardment and the damage, but you can still maintain a really high density plasma because it's controlled separately by the coil power. So, just to give an example of the difference in results between ICP CVD and PECVD, this is a graph showing wet etch rates. So with a wet etch rate, it's like an industry standard to tell you about the quality of the film. So it's like the density and whether it's pinhole free. So you deposit your film, you measure it in an ellipsometer and get a thickness, dip it in hydrofluoric acid for a known amount of time, and then remeasure it to work out the rate at which it's etched away. So for low temperatures, you can see that the ICP CVD in blue has much lower wet etch rates, which means that we're producing much higher quality films than with PECVD at these temperatures. Okay. The next important feature is the electrical characteristics. So this is important because if you're depositing a film to be an insulating layer, you want to have really high breakdown voltage. And with ICP CVD, we can achieve 8 megavolts per centimeter for deposition at 120 degrees Celsius. And if we compare this to the PECVD, we're working much more in the range of 6 megavolts per centimeter at over 300. So yeah, it's significantly better with ICP CVD, again, widening the kind of substrates that we can use and deposit onto. So just to give a side-by-side comparison of the kind of process parameters that we operate in, with PECVD, we like to be between 90 to 650 degrees. Most films are better above 300. And with ICP CVD, we work 20 to 400, but you can do higher if you want to. Quite a nice comparison between the two is the equivalent temperature. So a process at 300 degrees PECVD is the equivalent of 100 degrees ICP CVD. And then you can control the stress of both methods, and they're just process parameters. One thing, though, is with PECVD, you do get much higher rates than with ICP CVD. So it's important to tailor which one you use to your application. Okay, so just to summarize what I've gone through today, I've talked about two different methods of plasma production that we do. So there is PECVD with parallel plate capacitive coupling. Your plasma is generated in the same area that your substrate is in, so again, that can cause damage. You get higher ion density energies for a given plasma density, but there is the potential for plasma damage, and also you have to operate at higher temperatures to maintain film quality. And then we have ICP CVD, where your plasma is generated away from your substrate, and you can achieve very low ion energies, depending on whether you use your electrode power or not, and you can achieve very good film qualities without inducing damage. Okay, so thank you, and are there any questions?
Go.
So this is a more general question about ICP than with the or PECVD applications. But do you know what the history of the the prototypical ICP geometry is? I mean, so clearly you have this remote plasma you can create, but why not make it much more remote? So what are the limitations there in geometry for
I think a lot of it has to do with the mean free path of the ions. So for some processes, because the tool that we use for ICP CVD, we also use for etch. So I know that a lot of the ions are important to etch, and the further away you go, I think the fewer ions. Is that right?
Yeah. Any ion that reaches the chamber wall is lost. Any radical that reaches the chamber wall may be lost, but there's often quite a survivability in they maintaining the gas stream. So if you look at a tube style ICP and consider how many diameters of tube are you from the wafer, and is there obstruction in the way or free path as well? If you're several diameters away, and the flex cell would be an example of that, I'm expecting most of the ions to be quenched along the way, but the radicals are active. On the other hand, anything where it's big and open and not much wall interaction, then you get ion flux, and that geometry, it was a schematic, not an engineering drawing, but it was reasonably representative. You can get easily a milliamp per square centimeter of ion flux from those. Who knows the oldest ICP plasma reference? Any history buffs in the room? Give me the century. 1900s. Hittendorf, 1884 is the earliest I've found for an ICP. It was known as a ring discharge because his pressures were a little bit high, and so the bright plasma was actually a ring under the coil. So it's been around a while.
Along these lines, so you have plasma-enhanced ALD. What about plasma-enhanced ALE? Have you looked into that at all?
ALE, yes. The work I was presenting earlier today is plasma enhanced. It uses that same induction coupled plasma source, and actually we'll probably do the thermal ALE next as a possibility. Historically, we've been a plasma company and reached for plasma as our tool of choice to work on. But we're not addicted to it. If thermal is the way to go, then we'll use thermal.
But in that case, like, I guess I think that, I mean, is it possible that different geometries may still be viable if you're not worried about, the ion flux needs to be at some super high rate for etching, for instance. If you're doing some atomic layer etching, you may be able to get away with different ICP designs.
Yes, I have in mind that we might examine ICP with a more remote character for atomic layer etch. We have got a variant of the ICP CVD where we put some furniture in the way, and it's not quite a shower head. The holes are much more open because plasma would not transmit very well through a shower head. I mean, that's part of the point of a shower head. It keeps unionized gas and ionized gas separated. But we have seen a way of tuning up the process by introducing furniture. All done on PECVD. One more. Yeah, come back. Yeah.
What's the state of the art for PECVD, let's say oxide and nitride, in terms of the pinhole density or overall optical quality? Some metric when you compare it to, let's say, LPCVD. Are we able to get any closer to LPCVD quality for oxide and nitride by using plasma processes? Maybe not going to the low temperatures you're talking about, maybe staying at slightly elevated temperatures.
I think pinholes and the optical or density qualities are slightly different. Pinholes are nearly always to do with the discipline of looking after the tool and not having flaking and staying away from gas phase nucleation and all those things that promote particles. And they're you know, each tool has its own discipline, and we've got typically the PECVD oxides, you can deposit 30, we've even deposited 200 microns between cleans without having a sharp uptick in particles and pinholes. That is strongly dependent on the stress of the film, because the stress of the film is also the stress of the film deposited on the chamber above the wafer. And if you've got a high stress film getting deposited, sooner or later it's going to ping off. And there goes your particles. The density bit, there is this trade-off between temperature and plasma. You can trade one from the other. So it was, Hannah made the comparison that a 100-degree high-density plasma CVD process gave you the similar wet etch rate film quality to a 300-degree PECVD. Now, when I started out, we used to say, well, a 300-degree PECVD gave you pretty much the same wet etch rate quality as a 600-degree CVD process, because that was the dominant technology some time ago.
But can you carry that forward? Can you operate your ICP CVD at 300 degrees C and get a 900 degree C quality, temperature quality? That's probably not, right? But
Yeah, you've got exposed to more thermal oxide wet etch rates are.
okay, what about nitride? Like, LPCVD nitride really improves when you go compared to, PECVD. You get nowhere close to the optical quality. That could be the way what you're
Yeah. Is that hydrogen content?
Yeah, it's hard. It's mainly hydrogen content when you
Yeah.
talk about optics, but even in terms of density, I think it's not. At least my experience with nitride, regular PCV nitride at 300 degrees C, it's not nearly as good as LPCVD. So my question is, if you operated your ICP CVD at 300, maybe you get, I don't know what effective temperature that corresponds to.
I don't think we've done that test, have we? Have we done ICP CVD at above about 150?
No, at 300 degrees C, oxide is very close to thermal at 300 degrees C. I don't know about nitro. I track the problem there. Just got track off the top of my head.
Yeah, I mean, whenever we've done a comparison, if the film that's deposited hotter is always a bit denser than the film that's deposited cooler, no matter what the technique. And plasma helps a bit to bring that temperature down for the same quality. But yeah, I mean, we've got PECVD people who like to have a 500, 600 C table in there. They say, no, this gives us the really good stuff. But with PECVD. No, what we typically we wouldn't throw extra hardware on it, because actually the chamber's very busy already. It's quite a narrow gap. You've got a wafer on a table. You've got a shower head here. There's no more room to bring extra things to bear. What we do know is that higher quality films, which probably means lower hydrogen films, are deposited slower, because actually for any temperature it takes time for the hydrogen to evolve out of the film. And if you're throwing the stuff down, you're burying it, and inevitably you've got more left in there. But if you just go slow and give the hydrogen time to find its way into the gas phase, which it's very happy to do, then you've got a lower hydrogen film. So people, quite a lot of our users are not actually focused on a micron a minute or half a micron a minute. 10 nanometers a minute. We've got industrial users who say, no, that's our process, 10 nanometers a minute, because that's the layer with the properties we want.
And the mine produces quite a lot of UV and plasma. There's a correlation there or not?
It could be. Yeah, I mean, it's quite hard to decouple the thermal and the photonic effects. If we were interested, we could do it. You just put a cover slip, raise up a cover slip over the wafer and make it transparent or not to the photon wavelengths and see what happens. That kind of work's been done more on damage to low K materials, where there is a UV effect on the etch processing of low Ks. That's well known. For PECVD, I'm not sure that that's even been studied very much.
Over ICP CVD, is the nitride more stoichiometric than the PECVD counterpart, or is there even possible it should be close to the PECVD nitride?
Questions about stoichiometry. Well, the stoichiometry is controlled by gas ratios in all PECVDs. Is it easier to get stoichiometric nitride in ICP CVD? Well, it's SI3N4. Well, if you just go to refractive index. It's often expressed as refractive index tuning, and can you get a nitride at 2.0 or 2.1 or something like that. PECVD, that's pretty well known to be able to do that reproducibly. ICP CVD, I don't have the data in my head. Yeah. Okay, but it's a good question. Is there, if you wanted well-controlled stoichiometry, which technique should you go for? I think we should just note that one and see if we can bring some data to bear on it. Last ones for this topic. Yeah. Yeah, it's funny. Sometimes PECVD is everybody's done this and there's not much to it, but for some reason you all had questions for it. Okay.